Hello, and welcome to Woman with Bunny Ears, a Twin Peaks podcast. Today we will be discussing number, the philosophical concept or property or whatever we decide it is. But the point is, it's not like a movie or anything. It's a thing. And I am your host, Flashy Man, and this is your co-host, Jason.
Hello.
Yeah. So, Jason, what is number?
What's a number? No, not a number. Number.
Well, you can kind of answer. Each one is informative.
I suppose they're different. I mean, I think a number is, well, there's different ways of defining this depending on what you're doing. So there's there's number of things. I can count something. I have, I could have 7 daughters or something. And so I could count them, and then they would be a group of things that have some underlying common property, and then they'd be that number of things. But I could also just say, well, what about just the number? And I'm not counting anything. And that's kind of weird because that's not really like a thing or, something. But then I can start to manipulate that. Or I could say I have 0 daughters, which doesn't really make any sense. And that's kind of spooky. Or I could put them together and say, well, what if I had 1 more daughter and then I'd have 8 of them? And then we have all these properties, right? And this kind of sort of covers some of the ancient ideas of number. But then there's modern ones where it's some kind of a logical outgrowth of some more abstract things, and then we can kind of create these kind of useful sets of abstractions, and then we can map other stuff to these abstractions, and then kind of use statements about those abstractions that will then generalize into statements about real things, and then say useful things or useless things or something. But something like that is around where number is. I wish I had a better answer, but we'll come back to it. But really, I think my hot take is that numbers are love. A number is it's the union between wholeness and multiplicity. All numbers are the number one, and the number one is not a number, right? But it's parts being a whole. That's number, at least in my heart. That's my truth. So
how heartwarming.
Yeah.
What
do you think?
I think. Let's see. A number has something to do with quantity or magnitude. So it's an answer to like how much or how many, and apparently in a very precise way. But it kind of there are mysteries in there. Like, have I ever perceived a number? What is a number? So I think I've heard an account that a number is a property of a set and of like objects that you can have. And that set itself has the property of there being like 3 objects in there. But that's very strange because, I mean, I guess like no objects I've ever perceived are actually perfectly identical. So I guess you have to abstract them, and then you say like, well, there are 3 things that are kind of the same in there. And then I guess you can't really like get number on its own in some way. It's kind of like the property of being next to something.
Mm-hmm.
You can't just have it by itself. It's displayed when something is next to something else. So yeah, there are some mysteries there. Like, how precise does a number have to be? Have I ever perceived number? They say that when you look at something really fast, you can tell if there are like 5 things in it, but not like 10 things. Is that perceiving number? Does that count? And of course, we get to our very special friends like the real numbers and the imaginary numbers and the quaternions. Is a quaternion a number? Why or why not? Is an octernion a number? Some people will say it's like a number. So yeah, and we'll probably get to imaginary numbers in there and ask you whether or not an imaginary number is a number. Any of those pique your interest as things to pursue? Oh, also, I of course want to get like an account of ancient number which you've brought up before, but has never quite made sense to me what it's trying to say. So yeah, I've
I
also
guess we can start with sets.
okay. I kind of don't believe in sets in like a
Yeah, me neither.
mathematical set theory way. I mean, they're fine as mathematical objects, but why don't you believe in them?
I mean, I do believe in them and that they're really useful and they're really easy to talk about and really easy to teach. And I don't see a point in like so much of
Sure.
math, like modern math is built on this like set theoretical apparatus and it works and it's fine. And so, whatever sets. But I don't think of
Mhm.
number as like a less fundamental concept. Like it was like we all knew how to count things. And then some guy was like, oh, but like, how does this work? Like, how could I ground this into something else, right? And it's like, well, whatever you're
Yeah.
grounding it is just like less intuitive. Like, it's just like this thing you made up, and it's like, well, this thing I made up could like reproduce the numbers if I add all these like really complicated definitions to them and keep them all like forward, and and it terminates in this axiom of choice thing, which is I guess makes sense, but it's not like, well, it's not any more intuitive than counting like, well, 1 2 3, so I don't quite I mean, just in like the very like giga chat epistemology, it just kind of seems silly. Oh, here's Jesse. Hi, Jesse.
What's going on here? Why are you
Oh,
doing
we're talking about number for a
Podcast.
podcast on Twin Peaks, and we're talking about the
Yeah.
philosophical concept of number. And I was just talking about why I don't believe in set theory.
Yeah.
Okay,
We're kind of going over that.
In the book Landmarks of Tomorrow by Peter F. Drucker, he talks about how he's disappointed in our education for not catching up with the new concepts we have. He thinks the reason that we feel like professionals need intense and specialized education because we haven't. And he talks about concepts like algebra and calculus, the modern theory of number taught primary school. So and I looked up what he could find, and I found Wikipedia articles. You know how it's those. What's the concept of number?
What's the modern theory of number that you're referring to?
Well,
if there is anything
Well, I just know that he talked about there being a different concept of number that the people who are really in the know what they're doing. Apparently a number is a ring.
All that stuff.
But you don't like set theory. To me, a number
yeah.
Right, I don't have the philosophy of, and I haven't read Russell and Whitehead.
That's the whole thing about like rings and groups and fields and stuff, which I know very little about. I only know those words, and I think I've read their Wikipedia pages at some point. Those are kind of like patterns that you can see in a collection of objects. Like, you can apply this type of transformation to all of the things in this collection of object, and then they all turn into one another. Oh, and now you have an identity element, and so forth.
I mean, so specifically like rings and groups and such, it's ways of characterizing just any class of object. Like it's a way of generalizing things that like kind of look and behave like normal numbers where we do like normal algebra on them. And then you can get other classes of objects, right? So like I could add, 1 and 7, and then if I flip that, 7 and 1, I get the same answer. Or if I multiply them, I could flip them, do the same thing. And so you have these certain kind of properties in those operations there, along with, an identity element 1, a 0 element, etc. And if you kind of abstract that out to just those properties, then you get this generalized thing that then, well, our numbers are downstream of this, but then we could picture other objects that behave just like this, and then we can treat them like numbers. And so that's what a ring, field, whatever.
I think I get what you're saying. Sort of the general concept of trying to find a thing that is undernumbered, but
right.
But and you're saying it's primary because we can model it a certain way. What do you?
Mm-hmm.
And I know you're opposing, but
yes.
It sounds like the concept of number is already there, and we're talking about object.
Yes, exactly.
Is there a plurality?
So I think the concept of plurality is like deeper than that, and also why like some of the stuff fails to really like cash out as an explanation, because I think fundamentally like a number itself is it's this contradiction in terms, right? It's a plurality, but it's also one thing. If you count something, you're saying, well, this is 8 of a thing, and they all have this common element, but they're all different, but they're also somehow one, or else I couldn't call them 8. And
this is
in that,
close to the Trinity, though. Don't you like that?
Yeah. So this is how the ancients viewed it, or generally they had different concepts, but that was kind of one of their big hangups. And I think that plurality thing is just something that basically we price into set theory. That's like the modern way of viewing it, where well, it's a set of things, and somehow this setness is prior to plurality or encapsulates the concept of plurality. And I'm very skeptical of that. I think sets are just something the Anglos made up because they had nothing better to do.
Well,
I
if
think that part of
there's
sets is fine. But go ahead.
well, no, if there's a so having a practical application isn't necessarily necessary, but it would be a proof that this is a real thing. So Drucker felt like we could teach math much faster and reach advanced mathematics much faster if these concepts were under sooner. So do you feel like there is practical advantage to understanding anything in mathematics from understanding one of a sets of objects?
Mm.
Could there be?
I've always been interested in learning those things, but I guess because I never really learned about them very much, I can't really tell you. Except sometimes they'll look for an example of a group that isn't a number, and they'll go like, it's like a Rubik's cube or something, and then I think like strategies for solving a Rubik's cube often use like advanced math about groups and rings and stuff. So I guess it does help you with that. But Jason, if you have an idea.
So when I was in actually studying math and whatnot in college, I would have said yes, is that we could do these things at a young age and we should teach them in this highly abstract language. And now I'm older.
Algebra, pretty obviously.
If the kids are above a certain IQ, yeah, you could teach them algebra very, very young. But and probably you could teach them calculus. Like I think you could teach calculus to fifth graders, and as long as they're not, if they're minimally smart, it would be pretty easy. But generally, I think I don't know. My suspicion is that if you want useful math, it largely rests on heuristics and geometric intuition, and the algebraic abstractions really only cash out if you understand the geometry of it really well, which means kind of doing something either giving the kids Euclid or something even pre-Euclid that we're LARPing, trying to get to some kind of, because Euclid is okay, it's like Greek, they had geometry, but then Euclid's textbook is downstream of Aristotle's logical works where, okay, you have these propositions and these syllogisms and blah, blah, blah. And I think there's a pre-logical way of doing this where, you're still in the world of logic, but you're kind of doing things a little more heuristically, a little more freely. And the proofs aren't just I have this brute force mechanism to check if I'm right. It's no, you just have to kind of do it until you feel it and you can't see otherwise. And I think for children, that would be the best way to do it. Give them a compass and a needle, and at the same time, drill the shit out of them on just arithmetic. Teach them how to say multiply two different 5-digit numbers in your head, and that's some kind of big algorithm they'd have to memorize and just go through. And then but you should have them memorize the algorithms first, and then once they get to a certain age, you can kind of teach them several other algorithms so they see the underlying commonalities in them, right? Because these algorithms are always well, you have this many digits, then you split them over here and you do this and that, right? But they're generally very it's that same little pattern, and you get something called mathematicians call it number sense, which you especially get when you're studying number theory. But you just kind of, it's well, you see a number and you're just oh, that just feels prime to me, or that just feels it's the numbers acquire these extra layers of meaning as you just kind of have memorized so much that you get an intuition. Or analogous to this is I think you can't really teach history to kids without them memorizing just a bunch of dates and knowing how to fill things out in a map, because you could tell them all these stories, but you need something concrete for them to place these stories onto. And I think having that intuition with the numbers is the same, and it just requires tons and tons of examples rather than just drilling the abstractions. And then at that point, the abstractions come very easily.
All right. So knowing that 7 and 3 are 10 and 5 and 5 are 4, is that the sort of pattern you're talking about?
Kind of, yeah. You start to get that in your gut, or and you can really develop these things by say okay, somebody asks you what's I don't know, what's 88 plus 5, right? And you could have it memorized that oh, well, that's gonna something 8 plus 5, it's gonna gonna be something 3 at the end, right? But there's also a sense of intuition of well, the 2 in this 5 and the 8, they go up to 10, and then you've got 3 left over, and you're kind of and at some point you just memorize this and you just feel it. But there's also that sense of just breaking up all the numbers into their constituent parts, of just the simple chunks that kind of add up to 10, or all of the primes inside of them, like their prime factorizations, or just, all the various ways you could add up and get to the same number. You just start to see them. They just become more and more loaded, so that anytime you see one thing, like one operation here, you're saying all the different ways of doing it. And then you can start doing that symbolically, right? So there's classes of things of just like an algebra problem, right? There's just all these different kinds of problems, but then they all boil down to the same couple abstractions. Then you start doing, let's say, like differential equations or something. Well, there's a whole bunch of different types of differential equations, and you have to learn how to solve them all individually. But eventually you get like this deep intuition behind it, where you've seen so many, you just kind of glance at them and it's like, oh, well, that looks like linear-ish, and that kind of looks like this linear algebra problem, and that looks like this abstract algebra thing, and like it all just kind of rolls into one fuzzy thing, and you don't really have to think about it too much. And that mastery requires examples. Go ahead.
Excuse me. Sorry. This is Common Core, right? Is those examples?
Yes, exactly.
Except it doesn't seem like it's working very well, because these intuitions are the things that smart kids pick up by doing the drills. Because I remember that's how I got it. It's trying to skip steps and get all students having the understanding these properties of numbers. But do you think that step can be skipped? Like if Common Core math worked, that would be really great, but it doesn't seem to be.
I think Common Core probably doesn't work because of we're not ruthlessly segregating the kids by IQ.
I think you can definitely teach children who could be learning other math, like addition or whatever, about rings and groups and stuff, and then that would probably allow them to skip a lot of drilling, and they could go up and do like higher abstract algebra contemplation of rings and groups and stuff.
It seems like a group could go into factorization pretty.
Yeah,
and that leads right on from kindergarten shapes. The opposite sort of thing. What's an opposite in number theory? How's that? Is there something deeper about that concept?
I mean, there's so I think opposites are usually defined, or at least like an algebra, opposite's kind of like this deeper abstraction, but if you're just thinking opposite, like there's two ways to negate something, right? So it's, so you can invert something so that the operation goes to 1, or you can invert something so that the operation goes to 0. So like generally, if you're talking about like multiplication, right? Well, the opposite of multiplying is division. And so if you like multiply something by something and then you want to do the opposite, well, then you're doing that like so that they cancel out to 1. But if you're adding something, then you want to do the opposite of it. You're doing that so it cancels out to 0. So then the opposite is kind of based off like what the operation is centered around. And this is largely because you can't divide by 0. So,
although if what you want the children to do is be able to do those numerical problems, then I guess maybe they get like a little leg up by knowing, 1 over 2 is the multiplicative inverse of 2. But then, probably they still have to do all the work.
Well, in this
as well.
1 over 2 is the opposite of 2 over 1.
Yeah.
Well, the concept of every number being a fraction. But don't let me take you to rabbit holes.
Aren't fractions like a ring or something? Oh, well.
I don't know. But I mean, every number being a fraction is just as good of a segue. You've had your hot takes here, especially regarding diagonalization lately. If you want to expand on that.
No. That's far too airy. That's when we get to advanced numbers, we can contemplate infinity and stuff.
Well, I mean, it's kind of a legitimate question because in some sense, I mean, if you're talking about the concept of number and we're going to talk about the irrational numbers at all, then you're invoking infinity, and people have died over this. So it just, what the hell are we talking about?
I believe NA is a number. It's like the Trinity.
Nice. Could you possibly move closer to your microphone? It's getting. Oh, okay. I'm getting some room tone from you, which is, that happens. Let's see. So we were talking about sets and whether they're, I think you were alluding to earlier before this digression about modern number theory. I think you were alluding to a project that I think is most charitably interpreted in hindsight, I guess, as trying to use sets as like a model for numbers. As they say, that has some technical meaning that I don't fully grasp, but it's maybe I'm just using the non-technical meaning of it. And then you get these, you can build up your integers like the von Neumann ordinals, for
Yeah.
example.
Well, so I think there's two abstractions involved in building this up, which I guess is what, quote unquote, makes sets deeper, right? Is that you could have a set and then there's stuff in the set, but it doesn't have to be quote unquote ordered. And then the set can be ordered and then you can start doing things from that. And maybe there's some way of deriving this concept of order from like unordered sets. I'm not really sure. I haven't read enough Russell. But it just kind of seems like this circularly silly exercise where like the second you get to that abstraction of, well, the order of it mattering, you're just implicitly like saying, well, I'm just going to assign a number to each part of this, and then it's a number, and then it's like, well, I mean, what do you okay, actually, yeah, I guess you just derive it from like, let's say the size of the sets, right? And then you can start comparing sets, and then from there, boom, you've got this order concept. You can start counting, but it's still just it just seems circular.
It's funny. I've been in enough math class to know that when people get really serious about this, they're like, okay, we got these sets, and then we build a model of the integers out of these sets, and then when we want an ordered set, or like a list, you could call it, then we're just going to have like a set of the element and then another set that represents the number, say 1, and then the next element and a set that represents the number 2. So it's a very funny way of going about things. Whereas I'm over here in plebeian math land, and I'm like, yeah, we can just write those in a list. It's fine. I know that the next one is the next one. Anyhow,
I mean, I think that's capturing two pretty like useful abstractions, or even like kind of analogous to what I was like kind of gesturing at, like the ancient concepts of it. So, and forgive me if I just keep saying this, but there's one sense of like, it's that union of multiplicity and wholeness, which is, any individual number besides 1. It's like, okay, well, what is 2? Well, it's 2 things and then they're whole, but that doesn't tell me anything about its relationship to 3 or 7 or whatever, and that would be like, the sets there, as opposed to the elements. And then you have this thing that is the elements. Well, 2 comes after 1 and 3 comes after 2 or something. And then it's almost like a line or like a distance. And it's a distance relative to something. And, in some modern terms, we think of it as a number line because we're all these Cartesian oink oink piggies. And that's the only way we can see it. Right. But, and even if it's just the natural numbers and there's nothing in between them, well, it's still, it's, the number is firmly situated in the space surrounded by its lessers and betters. And those are kind of two different ways of looking at it in some sense that they're parsing out here with the sets. So
I kind of want to get to that, but first I want to finish my anecdote that I haven't even started, that involves these sets being built as a model for the integers.
Mm-hmm.
Because you have what I believe, again, are called the von Neumann ordinals, which is you start with the empty set, and then you have the power set of the empty set, and then you have the power set of that set, and then you can keep doing that, and that's how you get all the numbers. I think that's how it goes. And this is
what's
a suitable
power
model.
Set?
Oh God, it's like every subset of the set.
Oh, okay.
Yeah. That's a bad explanation, but if anyone's listening, they can look it up, I guess, and get a nice, pretty diagram. And yeah, so that's, I discovered that and I said, oh my God, I finally figured out what a number is. But actually, there's a different equivalent model of the numbers based on sets, and it's like 0 is the empty set, and then the set of the empty set is 1, and then the set of the empty set is 2. And I believe those were invented by Peano or something. And so if you were like me, foolish and naive, and you thought, oh, I guess numbers are this thing made out of sets, then you start thinking, oh, but which thing made out of sets are they? Oh no, I've made an error somewhere. Turns out numbers aren't sets in the end. And also, I don't really believe that you can have a set of the empty set in real life, which is kind of where I depart from a lot of, math stuff, which is fine. They can do whatever they want with their abstractions. But like, if a set is just a collection of things, which is usually how it's explained, then, your collection does not include another collection of no things. It's just that doesn't add anything to your
Is
collection.
there a set of impossible sets?
So there's
Probably.
Russell's paradox. I mean, which is like what the hell's the paradox?
Set of
It's like
all
if you have like
sets
a
Russell's paradox does not apply to.
Nice.
yeah.
That is kind of Russell's paradox. Russell's paradox, I guess, is, well, there's the set of all sets. Does it contain itself? And that has some sort of paradoxical
Well, there's a set of all
implications
sets that contains
about,
itself,
like,
that contains itself, and then there's a different set of all sets does not contain.
right, exactly. That one's the more immediate, like, oh, wait, does the set of all sets that don't contain themselves contain itself? Oh, no.
Well,
Oh, but if it does, then it doesn't, and if it doesn't, then it
there
does.
is a paradox shows that what we're doing is a language game and not a description of reality. Reality does not have Escher's waterfall.
Yeah, that's a pretty good conclusion to draw there.
But it does have.
So, what were we? Oh, yeah.
Recognize a waterfall that feeds itself.
Nice. Yeah, so I kind of wanted to ask, because this was sort of like maybe a debate, something that people thought about in early modern philosophy. And it's like, does the concept of, say, 7 include the concept of 3? Does 7 include 3, to say it in a different way that actually means something different? But
well, the concept of 7 does not make any sense if there's not also a.
Yeah.
So
But on the other hand, like, I guess maybe you could see 3 things and recognize it as 3 things, and see 7 things and recognize it as 7 things. Or, we could lower the numbers if you can't immediately look at 7 things. And then, like, not necessarily know that if you removed 4 of the objects, you would have 3 objects remaining. It'd be very strange.
Well, I mean, are we including, because it's like, okay, there is a sense where it's obvious that, okay, 7 must include 3, but what about, like, the square root of 3 or something, or, some, like, okay, at some point, well, okay, we're including this, we can include all the fractions as well, and then we can include these impossible objects that rely on infinity because there has to be some kind of continuity. But then even this doesn't make sense, because at some point, if we're talking about 7 things, then they could be things that aren't, like, couldn't be fractional. So if I'm talking about 7 donuts or something, I can't just, like, have half a donut. I can't cut the donut in half, and then, this is half and this is half, because the donut must be like a circle and be complete to be a donut. Unless, I guess, you cut them into circles. But, whatever.
7 inches are totally different concepts. You could imagine a system where 7, as in a number, where integers use a different symbol set. Where there's 2 kinds of numbers, and one is infinitely divisible, and the other, the things that are countable or ordinal. You can't take a square root of 2 place in a competition, but you can have a square root of 2 acre farm. That's an artifact of the unit of measure, and that sort of counting, the number line, is purely abstract. It's infinitely divisible, but no integer.
Well, I don't even know if you could have a square root of 2 in. I mean, like, it seems like, yes, in physics, like, physics wouldn't work, like, as we describe it, if we're not using, pi and e and these other irrational transcendentals.
You just measure out a square with one side here and one side there, and draw a line. You do a little geometry on it and stake that out.
I mean, it has to be square root of 2 of something, and that something will always be an imprecise measurement.
We relate it to integers. But do we have to? I think we do. And I know some suicidal atheist in the 1920s is out.
What?
Who?
Who did that?
I imagine that Bertrand Russell thought this.
Oh.
Thought this before. I don't claim to be making.
Yeah. Well, I guess in the background of all of that, I thought about whether 7 contains 3. And then I sort of came back around to, I guess, the sort of standard position where it doesn't really make sense to say 7 contains 3, even though in a different sense, 7 does contain 3. So that's fine.
Is smoke and fire, is that a property of wood that should be considered in a complete definite wood, or is that an external thing that shouldn't be considered as part of wood? It's considered as a relationship of plus, a relationship. Well, that's a whole model of cognition, that we're not worried about things at all. The only things that are out there are connections.
I guess there's just a model of essences there, and then that's, modern philosophy likes to deny the concept of just like, can you boil something down to, okay, well, this has properties, right? But then is there some kind of essential property that makes this thing itself? And those essences only make sense relative to other things that are then like a member of the category, right? So like a human being has certain, if you're trying to find the essence of a man, well, there's, some people are tall or short, or they have different numbers of legs or whatever. And, you could take these away and they'd still be human. And so at what point are they still human? And there has to be some kind of underlying commonality, which all members share. And in the case of
enough of it.
Yeah. I don't know. And I think in the case of number, like, what do 7 and 3 have in common?
Your birthday.
Precise answer to how much or how many.
Yeah, they have
a lot.
Yeah.
7 and 3 can have we as we understand 7 and 3, we can do mathematical operations on them that we can't do on cake and ice cream. Neither of which can be science to mathematics. There's new frontiers here, Jim.
Oh, let's see. Well, let's pick another thread. Jason, are imaginary numbers? Or wait, no. We should start at the bottom.
Mm-hmm.
Let's see. Are the natural numbers?
Yes.
Yeah, I think that one is pretty solid.
I don't think that one needs justifying. I think. Well, okay. There is a caveat here: is that if you're talking about the natural numbers, then you're already okay. So you say natural number. Well, you've already introduced the idea that 1 is a number, but that doesn't really make sense because it's not like a number of things. There's no plurality in 1. You've introduced the idea that 0 is a number, which there's no thing. Then you have the negative numbers, which don't even really make sense as anything except as.
Cool. Those aren't natural numbers.
Oh, they're not?
No, those are integers.
Oh, is that the distinction?
Yes. Also, 0 isn't a natural number either, but
okay,
that's kind of controversial.
Okay, I have. Well, I just know that sometimes they'll draw the little n, and sometimes they'll draw an r.
Right. Yeah. So, yeah, I mean, does a number? I expected the sort of like, oh, what's going on with 0? Am I right? But do you think it's sort of so like 2 is clearly a number, but 1 is maybe not a number?
Yeah, the ancients definitely do not think 1 is a number, or at least the Greeks don't. They just, it's, you can use it in operations or something, but it just isn't like philosophically, it's not a number of things. It's not the abstraction of that as being the number. We use it.
Used to arrive at a.
Yeah.
You can pull a useful number out of it, and pull useful numbers. You can use imaginary numbers for polar coordinates. But you could point for a polar coordinate. And so is an imaginary number the same thing as a counting? I mean, it can be. And so we call it a number out of respect for what we can get out of it. You don't call pointing a number because you can't really turn that into something so precise.
I'm sorry. I think that's kind of what I was getting at with the negative numbers is that like they only make sense. Like, okay, we're abstracting out this idea of like plurality, and the negatives only make sense once you've added in the subtraction operation in there. And then, well, here's all these useful things you can pull from there. And then you could pull these into the addition operator or the multiplication one. And, you can start doing that. But at this point, it's not just counting. It's, well, here's this other stuff you could do that's kind of generalized counting and its opposites. And then we start adding all these numbers into it. And the imaginary ones are the same way of essentially they're a way of describing rotations. They're polar. But again, you could point. And so we've gone from this number of things to, well, what if we stretch it, or what if we move it around, or what if we do that? And well, now we have to have extra numbers to account for that. And at that point, well, is that really a number? Or are you just kind of, describing ways of distorting numbers?
I see what you're saying, because you could have like, a point on a line, and when it moves forwards, it's a moving point.
Mm-hmm.
Then it's that's like a positive integer. And then when it moves backwards, it's like a negative integer. But I suppose you could just have like a pair of integers, and then if it goes one way, the first integer is there, and if it goes the other way, the second integer is there, and the other integer is 0. Which I suppose if you got into real boy math, they would tell you that like the negative numbers are, an equivalence class of pairs of integers like that. or something.
They're a bunch of nerds.
So negative numbers are really tightly tied to finance, recording debt, and I think a way we can conceive of them is as requests. You know, we're in the cave, and I say, Jason, give me to dear heart, or take to heart, and I can say, Jason, give me infinity rock, and that's a real thing that I can say. It's not an achievable request, and so
that's just moving those points forwards or backwards from
right.
you
And
to
so
Jason.
what I'm saying that there's a connection to a real thing here at every point, or we would not do it.
Well, interestingly, so like I think what you're kind of gesturing at is double entry accounting, which is ubiquitous in the modern age, right? There's debit and credit with every single transaction, but this was not invented until about the maybe like the 13th century, right? And then before that, we just don't, I mean, there are negatives in there, but we don't have that neat bookkeeping of, every time I'm credited something, somebody has debited something, right? And the money's always moving.
Something that exists, and you can do some clever geometry on it to figure out how much of it that. But it's not a thing that's the opposite. It's not a thing that's clearly connected to its opposite, a debit and a credit.
Yeah.
But it seems on. I figured it.
Thinking about.
Oh, go ahead.
Oh, go ahead. Oh, okay. I've been thinking about this thing you've been saying where they thought 2 was a number and they weren't so sure about 1, and they probably didn't even have 0 yet. And I think I would like to know who said that, first of all. But I guess, that makes sense linguistically because, 2 is like an adjective you can put onto a noun. There are 2 birds. And then you would just say, there is a bird, or if you're speaking in a language that doesn't have articles, you would just say there is bird. But and that's an interesting way to start. But I think in terms of answers about quantity, 1 is pretty solidly a number.
The Chinese mystic Gong Sun Long would confound kings and by telling them that they had 3 ears because Chinese does not have a plural. You have your left ear, right ear, but you also have ear that they couldn't.
I've heard that. It's very funny. Now I'll tell you about how a white horse isn't a horse.
Well, that's theory, isn't it?
Just to explain that one, it's because white horse and horse aren't synonymous, and if you have a black horse is a horse, but a white horse isn't a black horse, that's crazy.
Well, it's this concept.
We live in the classical era.
Horseness of a goal to reduce all numbers is Platonic ideals here. Is there, if we go to Plato Planet, do we see a white horse and a black horse, or do we just see a astoundingly colorless horse hanging out with colors? I will say that hylomorphism
that's an interesting
itself
question.
seems to be an artifact of language.
Yeah, so what you were saying about articles was interesting, Flash, and I think it kind of ties into all this. And also, as for who said this thing about 1, I'm largely getting this take from Jacob Klein and then some kind of later Heideggerians who are basically just copying him. And he's just getting it from just his readings of Aristotle and Plato, but largely Aristotle being like, oh, this is actually what Plato meant by forms, and what Aristotle says is that it's number. But I think there's something in the concept of articles that is kind of important here. I'm sort of losing the thread, but there's a distinction between like the bird and a bird and birds. And then this difference between 1 and 2 is somehow downstream of that, where, like you said, it's like having 3 ears or something. Like there's not, there's something about that concept that is separate from merely plurality or specificity or like, or not even specificity, like the difference between and the, where is, well, I know there's other members of this category, of this set, and I'm just pointing to one of them, it doesn't matter which one, versus, well, here's the thing, and it's of a category, but it's the specific one that I'm referring to. And then there's a plurality of it, of some number of it, or you could say, well, all of them. And then you could start counting. And there's some languages where they don't even like have numbers, and you can't really say like a specific, here's how high or here's how many. They just haven't developed that abstraction yet. But at least the ones that the European ones did. And so we have that, but it's still this. I think that is somehow downstream of the way we're using articles.
There's an articleness from which our language has to pull from, or it could be that every relationship in our language has an emergent property of, and so what really underlies it is just that there's a relation, and because they are how they are, we have rather regular connection make from, in the same way that wood doesn't actually smoke and come from. There sure is a lot.
Just thinking, well, obviously, you can't have the articles just mean singular, but I guess you can say the birds. So, or maybe that's like implicitly the singular group of birds that I am discussing, even if it's all the birds.
I think it's the latter, yeah.
That's
Unless you
interesting.
specify beforehand that you mean all the birds, in which case, yeah, it's context dependent.
The average bird.
Yeah, but that, it seems like the articles are downstream of the singularity and plurality, because things are singular, or there are more of them than one, and then
yeah, but then
just sort of
the precision of plurality is downstream of that. So there's a singularity, there's a plurality, and then after that there's a specific number of plurality, and then this would mean that number is not, it is downstream of something that was already distinct from the singular, so one wouldn't be a number.
Well, do you think that going this linguistic route is actually promising as a way to investigate the numbers?
That's the only thing that we've ever investigated.
Yes.
Why? Well, you can look at some things.
But then we have to talk about them.
On this podcast, sure.
Yeah.
But in your life, day to day, you can just look at things. And then later when you have to report them, you can speak in any language using any crazy constructions you want. And it's not necessarily going to make much of a difference to what you're looking at or operating on.
Well, so this relates to a question I've always had, which would normally seem too specific to relate to such a philosophical point, but now I actually do think it's related, is that I find it very odd that there's a distinction between kind of like a shape rotator intelligence, which is good at mathness, and a word cell intelligence, which is good with words, because in some sense, being good at math, sure, you have to visualize things, but we've reduced math, post 15th century, post Descartes. We used to just write our math out as Latin sentences, and now we can, we have this very efficient symbolic language that we manipulate, but it's a syntax with a grammar, and the numbers are nouns, but we have other nouns that we can, put in there, and classes of things, and vectors and fields and algebras and tensors and whatever the hell you want. And then we have these different indices and rules and bits of punctuation, right? But fundamentally, it's just, you're just moving things around in a grammar. And then when you learn a language, some people, you can learn a language real well, and then they will stumble on grammar. And this is especially evident these days because nobody learns grammar. And I've always wondered if, there's something about grammar itself that is fundamental to what it means to be a shape rotator, outside of just your ability to, manipulate literally shapes in your head, that this and kind of abstracting out syntactical intuition are somehow the same thing as applied to language. And then, something like word cell intelligence is more of just the raw associativity that you have between nouns, if that makes sense.
Yeah, I think I see what you mean. The word cell, as it were, can keep a lot of these related ideas in mind. But then how do you tell which ideas really should go with which other ideas? Maybe it's some sort of shape rotator type talent.
Shape rotating is kind of intuitive because the words are on the other side of the brain. To describe rotate shapes, to talk about them, you're no longer shape rotating. Thinking about that, one way to rotate shapes in the real world is build a bridge. That'll have a really powerful effect on everything. I think there's not so much difference between shape and, but we might have. Am I getting into Chomsky if I say there's specialized brain structure, different kinds of the same?
Yes,
you are, but that's fine. Get into Chomsky if you want to get into Chomsky.
Well, I kind of hate Chomsky, but I kind of like him. I don't know. It's hard
the
to.
world being spoken in.
Yes. Well, that's. I think that's another highly relevant tangent. Is that the ancients are quite logocentric, or if you're a Christian, you think God is literally He's the Word, right? Whereas the modern idea of reality is, it's mathematical physics, and it is, what we can describe with that. And, maybe, in some obvious sense, well, this is a language and this and that, but I don't think people see it that way. I think people just see this is just, the world is just math somehow, and that is somehow not a part of the logos, or that is somehow the logos as we understand it is downstream of that, is all fields are downstream of mathematical physics now, in some way, except for maybe math. Whereas before, everything would have been downstream of theology, or, really like philology. But, it's some kind of a linguistic way of touching God. And now it's, we can mathematically describe everything he does in terms of these
That's
brute
just a
laws that are
grammar, though.
always followed, even though they're probabilities, and it's all fake,
logos
and
that
blah,
you
blah,
can't write
blah.
poetry.
Yeah. I think you can write poetry in
I
it, to
love
be
poetry.
honest. I think a lot of I think the laws of physics are some like poems written by God, but that's a whole different subject. But they are very beautiful, strikingly.
Is that the idea of logocentrism is still useful, whatever the universe is made of, because the word is followed by action. There was light, most passive of voice, but it's not like everyone. It doesn't say everyone said there was. Everyone agreed that there light had to come. So the plan, the blueprint precedes the building. Precedes action.
Yes. Well, I think also proceeding precedes the speaking. Like I think there's something in that to where there is no temporal sense until like in the beginning, right? There was this. And then you can start talking about things in like a past tense, a prior tense, but you can't do that until the beginning. So somehow, even the concept of time itself is downstream of this light that is being spoken into being, that is the word, right?
Somehow outside of these concepts of togetherness and partness. Maybe what we see as the Trinity is kind of a three-dimensional cross-section truth that is comprehensible.
It is certainly a truth that required a higher level of metaphysical abstraction to not be just sound implicitly ridiculous on the face of it. And it took all the councils to work that out, and mostly in response to like heretics. No, but it's, it was enough to basically define themselves against various heretical schools, right? And then, we can make these very precise statements of like what the Trinity is not, and then we can define it according to that. But it's still fuzzy.
Talking about.
So I think the one good example would be just like, I'm forgetting which one it is, or maybe Barcelona, but it's whenever they just work out just like the logic of the incarnation of being like both fully man and fully God, and these being kind of separate but the same, which is not quite the Trinity concept, but even just grappling in that in Christ, I think that requires just like it's a metaphysical leap in how you think of number, which then allows for these extra abstractions. I think maybe 1 and 0 and such. I mean, maybe that's kind of I'm reaching here, but there's something in that kind of summons out the modern logic, I think, maybe.
Super up to date with the actual decisions of all of these councils. Maybe I'll get to it in the next couple thousand years. But they certainly seem to be like, they sure want to say a lot of things that really conflict with what I believe about number. Like, I don't know that many things about 1 and 3, but I'm pretty sure they aren't the same. And also, I'm pretty sure that one thing can't be two things that are both fully it, which isn't even really a point about number. But it sometimes seems to be stated, as though it has some sort of numerical significance. Like if Jesus Christ being fully man and fully God is a sort of thing, some people want to say 50% man, 50% God, or something. If you want to work in that metaphor and you say, yes, it's 1 plus 1, but it equals 2. It equals 1 instead of 2. That would conflict with my intuitions. Also, another non-number example, it would conflict with my intuitions if an object were completely red and also completely blue at the same time. But hey, maybe, the last time I looked into what they actually meant by that, it wasn't really super apparent what they meant by it. Almost as though they were just defining more words underneath themselves as they went.
Circular and square.
But I'm no theologian.
And you could imagine this being shorthand for whatever the concept is. It looks like this.
Yeah. So I don't think they're gonna help us. Those
I'm not actually
councilmen.
a Trinitarian, but I'm imagining if this sort of thing could be used to sort of describe the indescribable. If there really were somehow. There could be a cheat like different.
Yeah, I mean, in some Well, I mean, in some very obvious sense, and when we kind of have described the indescribable through the advances in physics, so now it's like, we very mundanely understand that, like, oh, well, if you move really fast, time slows down, or that, gravity is just this curvature of space, and then we can describe these, geometries that are not our standard geometries, but this is actually the world we live in, or that there are literal holes in space and time that literally our math breaks down, and we cannot describe them, but they're real, and we've seen them, and they have these properties, and then we describe them.
And so a hole in
Yes.
space is an
Impossible,
impossible
certainly.
concept. Space is whole. It is a hole. We can, when you say a hole in space, you imagine, space is actually a substance that can have space within it, creating a layer of abstraction around it. And so we're attempting, we describe an impossible concept as a clue to an indescribable concept.
Yes.
The pedantic need to point out, in case anyone was wondering, that a black hole is actually the opposite of a hole, being so incredibly packed with matter. And I just think that's interesting.
Well, so I don't know. I think I could push back on that, and that you can have black holes that are actually
go ahead.
They're really not that dense. Like you can have denser things in a black hole. Like I think a neutron star is just denser. Actually, I think most stars are. I don't know off the top of my head, but they reach a certain kind of a uniform radius that is like not intuitive, like it's like, and maybe like inside of it, right? Then it's like, well, the stuff inside isn't uniformly distributed. Then you can have like these crazy densities inside, or maybe it's just like another universe or something, who knows? But, well, I think some people know, but the, it's, they're a hole in space insofar as like, if you're an observer, then you yourself can't cross into it. You can't, you're just going to approach it infinitely without ever getting there. It's like this asymptote, and it's just a sphere.
Imagine other places where someone says, well, because our math breaks down on this subject, reality itself breaks down on this. It doesn't really seem on the face of it like reality itself is breaking down inside of an event horizon. It seems like our math sucks. Like our math doesn't properly describe it, because we know that our math is complete. We use, we use GPS and flash memory in our phones at the same time. That's general relativity, quantum mechanics working together. You shouldn't. And so find this back in the concept of impossible things. This is logocentric, starting from the idea that our words are describing, that our math is describing true concepts. Since our math breaks down, we add epicycles to the math to work, and so we assume there's something that cannot work, like something asymptotal in a world or in direction.
Well, I mean, I agree with you, but the other possible interpretation is just that, well, our concept of space itself is, something of like part of this shitty math. And because this concept is breaking down, then, I can say a hole in space without it necessarily just, implying something indescribable or unreal. It just means like space itself doesn't have to be that coherent. And like, I don't know. And I mean, I have like a hotter take of really there's just Kant, right? But, there's a sense where it's like, well, space and time don't really exist. They're just kind of like these mental projections we're putting on stuff because it's easier. But there's, all these different, like if you're going to mathematically describe reality, then there's no reason why like time has to be special. And my deeper suspicion is that time itself is only kind of it's like a regularity in like all of the other ways of expressing things, to where we can see these repetitions. And then we've seen like the most common repetition, which is the sun. And then we started calling that time, and then we've kind of abstracted from there. But time itself is kind of, it's just an artifact of like this regular thing that we happen to sync up to and move through in this kind of omni-space, but we're not actually like stuck in time. That's just like our perception. Or like, for example, like there's these metaphors of like, well, the mind's a computer and it's doing this and that, right? And well, generally a computer computes across time, but you could also have a computer where just you're drawing the logic gates on sand, and then it's computing over space. And so, you just need a certain extra dimension to kind of do the work of that quote unquote computing time. And so, yes, exactly. And so there's no reason why time itself has to be special or even real if it's really just kind of these recurring things in the rest of the coordinates is, part of my take. And then, but we're so, because we're stuck in space and time because of our perception, then we have to have this concept of number because it's kind of baked into that somehow. So we've kind of...
when we celebrate the new year right now, we're not celebrating it like our ancestors. They celebrate return of sun. They celebrate a new day. And we celebrate increment, a number. We celebration. Things changed. We've marked out all of a number line. The ancients were still celebrating year, but they were celebrating that we were going to have the same year.
There's a sense where that's like kind of a microcosm of everything we've been talking about number, and that, we have a certain way of looking at something from which number is downstream, and then going from the ancient world to the modern world, instead of that, number being used to keep track of the thing is just one more number. And then we just have this sea of numbers that we're drowning in, kind of divorced from their original concepts, and the concepts or, the things themselves. Well, yeah, that's the thing, but that's kind of the quaint way of looking at it. And the real thing is the number, is the increment, and then the increment is just kind of this meaningless thing that we use that, we kind of can tie into certain contexts as, well, we care about the date since Christ or something, or we care what month it is and this and that. But these just act as social coordination points or ways of pointing at things in history for, basically useless knowledge. And then, because this number has because number has kind of transcended the world, then, we do too. And then the world itself is kind of superfluous, and everything is number, and everything is code and digits, and, the money is, tied to nothing. It's all fiat, et cetera, et cetera. Instead of loving your wife and dying with her, you have a spreadsheet of all the partners you've been with and how long it lasted and how many times you fucked or something. There's a sense of, we could bleep that one out, but there's no cursing in this podcast.
Drilling kids so that they understand the number line. Because the number line is a very powerful way to conceive of history. But I believe the Greeks didn't worry about that. They kind of divided things up in the past, and the ancient past, and mythic past. And we see that in the medieval wonderful flattening of everything till you have art that doesn't have any perspective on purpose. You have the Battle of Jericho and everyone goes in chainmail. And that's it. Our number lines separating from history, rather than we consider the Battle of Jericho to a thing fought with rifles and plate carriers.
Well, I have to say, divorced from the metaphorical point, which of course has value to it, I do think that time does progress forwards. Obviously, that's redundant, and it does progress at sort of a uniform rate. Although, of course, that too is a redundant statement of it. And so it really is.
Because you could take the Greek
concept
even farther and
right.
say that the American Revolution and the Battle of Jericho are equally past, because we can read about them in books. They're in the set of things we can read about in books. And here's the medievals again. They read about it and they read the Bible and they don't see contradiction. They don't care. It's just the settings that are written by the ancient. And we think about time as progressive within this frame of duration. But it's been the same year every year. Every year has started with days be short, days were short again.
Speaking of days, actually, you could ask like the same thing. Like, how many days has it been since the Battle of Jericho? And back in the ye olde times, maybe they didn't have a very good way of answering that question. I guess you would have to, do a bunch of investigating, maybe add up some years
Leo,
and so forth.
Was at the sunrise, and so that's when we light the candles.
Right. But it remains the case that there were a certain number of days in between the Battle of Jericho, which I'm just assuming happened. I don't know. Probably it did. And then, a certain number of days between the Battle of Jericho and whatever medieval peasant. And that's a real fact.
Well,
and they had no reason to track that fact or do any reckoning about it.
I'm trying to think of examples. There's changes in attitude that can be tracked, and we don't do that with a lot of precision. We don't. I mean, the trackings. But if we did, you might record history in a way that tracks it, and a lot like those maps that change countries' geographical size based on their population. A balloon around trails off into. And it would still be a fact that you could measure, but it would be downstream of the logo, in that it is made. We're talking about the.
What do you mean by logos there?
That it's not really a distinct property of reality. I'm not saying I totally believe this concept. That things aren't necessarily distinct property of reality. We use our language to separate facts about the changes that have taken, and we can very reliably measure them on an atomic clock. But the clock comes first. The calendar comes first.
Well, I don't really know what you mean by comes first.
As a useful concept.
Yeah, sure.
And we can measure other things.
I mean, what are you gonna?
We can measure things with great foreshortening. And so a practical account of this would be the elimination of Whig history. Whig history is based on the number line. As we can see the numbers progressing future, the duration on them increasing, we can see that in 8,000 years, our years will have 5 numbers rather than 4 numbers.
No, they'll actually both have 1 number apiece. Got you there.
Oh.
You've used the term number for digit. You fool. You've fallen for digitism.
Our number theory will have advanced, and our years will
but
include
go
5
on,
different concepts.
If you had another point you wanted to make.
Well, the line will go up.
My God.
You graph how many years we've had, and that will go up. And I feel like the optimism of Whig history, that our society will also go, maybe with a couple of hiccups, but since it has in some metrics gone up recently, will continue so sort of in this fundamentally leaves us prepared for shocks and dark age, potential zero, because we year as always. I'm just filling space till Jason's.
Well, I don't feel this is helping us investigate number itself, although point taken. Nice. Good extemporaneizing. Oh, no, I've said that wrong.
I like all of these kind of object level, like let's say like even historical or metaphorical digressions, because I think the concept is, like same thing you were asking about, like, well, is the linguistic angle helping us get somewhere? And it's at some point it's like, you're up so high in abstraction space that you really have to, you have to come at it from certain kind of angles of like, well, where is this actually used? And then kind of derive it from there. Like we didn't start with some pure concept of number that we abstracted out and then we just started using it. We started using it first and then the abstractions came later. And now we have fucking, set theory in this stuff. But, it's all quite intimately connected. And I think each digression illuminates something, even in just how we view the digressions or how we disagree with them or how your two intuitions clash. I think all of that is quite
know what's an intuition,
fruitful.
And what's a tradition.
Oh, that's true. Yeah.
And what I might be believing out of habit that might just be a handy rule of thumb to the ancients.
They seem like they're not, depending on what form of the word intuition or sense of the word intuition you want to use. They're not like completely non-overlapping concepts. You could have an intuition for something because your tradition told you about it, or you could have an intuition about something just because that's how humans work, or because you've just seen a lot of things by yourself and you formed a subconscious hypothesis about how they go, And we certainly have a lot of traditions about number, let me tell you. I do sometimes wonder, what would I think about number if I had never been taught about it? It's hard to say. I guess probably an animal can perceive multiple things at the same time, although I'm not even sure if I can perceive multiple things at the same time. Do I just perceive them in sequence? Yeah. Well, that gets you into like logarithmic utility functions and stuff, which is really interesting. Like, especially if we want to consider number from the perspective of like magnitude or intensity of like light. In some sense, our perception of light is logarithmic in that you have to double the amount of light to get one more perceived unit of brightness.
Concept of logarithmic numbers separate from counting numbers, maybe even using a different symbol set. Base, I've heard of like base e, base log 10 sorts of counting sets, but with that, I feel like this sort of thing could actually give us an advantage in figuring out how much with logarithmic numbers.
I think we do that with just base like log 10 or just like scientific notation. Like it really just depends on the context you're talking about, right? But if you're like in a like just the context of physics, you pick some units and you have some kind of base intuition of what those units are, and you can usually kind of develop that intuition by just working around a lab, and it's like, okay, this is what a volt is, and here's how fast light moves or whatever, and then you set certain things to 1.
you could imagine kind of being at the cognitive state where we could have labs, but we could also not really count without help. But I feel like we would, because you can, like you were talking about a calculus intuition.
Right.
You can have an intuition of rates of change, just like you can have an intuition of a number set of 88 and 5 having this sort of thing that would be very practically useful.
Yeah. I mean, I think the greatest scientist who ever lived would be Michael Faraday. And he basically works out all the laws of electricity without knowing any math. But basically, the entire modern world is downstream of him and his work in the lab.
Era maker.
And
tell you that now.
Yeah, I mean, he is the era maker. I think he's probably, in terms of like just people to where if he hadn't lived, the world would be different. He's probably number one on the list for the past, let's say 150 years or whatever.
Well, I mean,
died exactly.
The concepts of electricity,
at least in terms of scientists, maybe, but
the hydraulic metaphor is an ugly kludge, and so
yes,
if there could be a symbol that a
well,
metaphor
I mean,
that
like,
we could use for electricity that would cause us to understand those concepts better, I feel like that would expand other areas. Also, very frustrated by electricity.
Yeah. I mean, I think he did a pretty good job working these out in some sense, kind of thinking of it.
Right, we can work it out.
I'm not sure if he was explicitly using the fluid analogy or how much of that is like from Maxwell making it mathematical down the line. But but without the math, like he had it all down.
Right, there's a set of fractions.
Yeah, but like his formulations of it are intuitive, and I think he was, and they're largely just like proportionalities of like, oh, well, like when I do this, this does this. And basically the inside is like, well, if I spin this magnet around, there's some current going through this wire. And then he figures that out, right? And then like, boom, we have the whole modern world. And, and he kind of gets, there's a few other rigorous mathematical laws that you're getting besides this, right? But it's just that very, spin thingy. And then if I touch this, it's hot. And then we have the math with, 20, 30 years later. But he didn't need any of that to get to this insight. It was the mathematicians that came later and did that. But, even without the mathematicians, you could start, oh, well, I spin this magnet, I have this stuff. Well, you could start building stuff, right? Like you wouldn't actually need to know the difference between 9 and 13 or what a vector field is or et cetera, if you just had kind of Faraday's original formulation of those laws, which were just kind of proportionalities or just simple like cause and effect in the real world based off intuition. And he discovered it without knowing any math, right? So you didn't even need it to derive these in the first place. It's just, you just play with the lab and it just comes out.
I'll give it to you.
Yeah.
And interesting talking about
it makes a lot of sense
versus science. You don't need to do mass equations with brick on brick and off. As I understand it, that's the way that we catch a ball in flight without doing calculus. Make slight adjustment as the ball changes
right.
view.
Yeah. So here's a hot take I had maybe like a couple weeks ago. But I think this kind of relates to your initial point, Jesse, about maybe like teaching kids like groups and fields and stuff, is that I think largely the heuristics we use for getting through the world, they're based off us finding mathematical symmetries in something to the point, where a symmetry is something that stays stable, or if you do something to it, it stays the same. And basically higher math is largely looking at a system, finding its symmetries, and then finding a way of just describing it in terms of kind of the stuff where, okay, if I do this, this stays the same. If I do this, this stays the same. You kind of put this all together. And once you do that, you make something called, you call it linear, which means that, you can start doing normal math on it and just get easy results that we already know how to calculate. And I think largely like when you're doing that thing, okay, well, a ball's coming at you. Well, how do you know how to catch it? You're not doing this complicated physics equation in your head. Basically what you do is you run until you're at the same speed of the ball. And then that's when the ball's standing still. And then from there, it's very easy to kind of automatically figure out your trajectory and where to put your hand and stuff because you've removed all the change from the situation. And I think the same is true of, let's say, like social roles, like gender roles, kind of the way we think of hierarchies, the way we think of just space in terms of landmarks or whatever, is like we find the thing that doesn't change and then everything else is in reference to that in terms of the regularities in that. And I think there's a sense of where this is the more like maybe what that guy was talking about, if, well, the kids would get the math better if we taught them this. Well, what a group is, what a ring is it's based on symmetries. It's based off, there are these certain useful invariant symmetrical relationships of, okay, I add this to this, and if I change the order, it doesn't change, right? And then if you have something like this, it looks just like the numbers doing addition and subtraction, multiplication, etc. And I don't think our brain is wired to compute anything more complicated than that. I think we only move through the world either in like mathematical abstraction space where we're building rocket ships and stuff, or if we're just walking around cooking breakfast. In both ways, we can only compute things if we look at them, map them to something linear that kind of looks like it can be worked out without doing anything too complicated because we have little tiny working memories. And then we start moving it on that. And those are our heuristics, and that's just all of reality. That's my hot take.
I agree with a lot of that, but surely, surely you can sometimes do non-linear things, right?
Yeah, we're just not good at them.
Fair enough.
Like-
Yeah, I agree.
Yeah, so like if you take largely if you have anything non-linear in math, what you do is you make an like the standard trick in physics and all of physics is you have some non-linear looking thing. Well, we can make a Taylor series or Fourier series, which is either it's an infinite series of just powers, so x plus x times something plus x squared times something plus x to the third. Make that infinite, and you can map any equation that satisfies certain properties to that. If it doesn't satisfy that, you can do more complicated ones like adding all the the negatives in there, or you could do a Fourier series, which is just sines and cosines, which is really just adding up e to the something, and then each of these has individual coefficients, right? And the neat thing about either of these is that the bigger they go, the less they matter. The first term, that's just x, and then the second term that's x squared. Generally in a series, what's going to happen is that the higher the power goes, the less the thing it's multiplied by matters. And especially if the thing that, if you can kind of cheat your units so that, the thing that you're making into a power is less than 1, then each time you're multiplying it out, it gets smaller and smaller and smaller. So you do this little trick. And then, magically you can turn anything nonlinear and complicated into some adding of linear things that are all separate. And then you just look at the biggest ones and you say, okay, this is close enough to the answer. And this is how we do quantum mechanics, classical physics, fluid dynamics, like you name it. This is just everywhere. And what this means practically is that everything in physics just boils down to the, having a mass on a spring or something. It just goes back and forth because describing that mathematically would just be the potential energy is x squared. It's just a parabola. And so, we just pretend everything's a fucking parabola and then we go from there. And that's how you solve a nonlinear problem.
I've heard that before, possibly from you, but also from other people.
Yes.
And I have always wondered, correct me if I'm wrong, but a logarithm is non-linear in this sense of linearity.
Yes and no. A logarithm is actually kind of magically double linear.
Whoa.
Because you can multiply stuff inside of it, or like add things inside the logarithm, or add two things in the logarithm, and then you can kind of like take them out of the logarithm or move them around. Exponentials are the same. So e to the 1 plus 5 is equal to e to the 1 times e to the 5. So if you're adding stuff inside of it, it's equivalent to multiplying two of them. And so then that's also why we like in physics of just making everything e, because then you can do this magic stuff with multiplication or addition. They're kind of equivalent. And then logarithms share this property. So in a sense, they themselves they're not linear, but if you could just calculate a logarithm, right, and we have just a logarithm table, we've already figured that out, then you're just doing that over and over again if you can make it into a series of logarithms or whatever it is. And then that would be linear.
All right. So, yeah, that makes sense. So my question was are physicists baffled by logarithms? Why don't they use them more? But they're actually, logarithms are super easy and they use them a lot.
Selecting
for
problems
because they make other things
linear easily.
Okay,
and
that's
ignoring
interesting.
Things.
That's my strong
No.
Talking about
we just cheat,
relationships
obviously.
that could be intuitive, and how everything in electricity, increases by a square or is divided by the. I think other people covered this a lot. The idea that it's found a bunch of easy relations. The code of the unit might just be an or numbers that are so.
Yeah. Let me look up the name. 1 second. There was that thing I posted the other day, but it was it's this function that Scott Aronson talks about. What the hell is it called? It's basically a function that defines the limits of what is computable, so that it has this property to where it's called a busy beaver function, right? Yeah. So it's it's like all the different like ways. It's like the longest string a Turing machine of that size could make or something. And the thing about it is like, well, if you're going to compute that, because like any computer would be like analogous to a Turing machine, then you can't actually compute it. You just have to let it like run its course, and parts of it are not going to be computable because some of them are just never like, they're just not going to have like a string ever appearing. So it might just run forever and you're not going to know. And so because of that, it has this magical property to where you can think of any function to where if you can describe it in English, like in terms of the logos, if you can make a description of it, well, if I take the power of this, the power of that, and blah, 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 and you make it like, take any input and you get some cartoonishly big output, anything you could possibly describe linguistically, at some point, this will start to grow faster than it because it's just, it defines the boundary of what is and isn't computable to where any number, like any function that gets an input and gets to an output that's, bigger than this, because this one's based on what you can, like the maximally big thing you can compute with that input, anything bigger than that is just, it's not going to be describable by anything you can describe. It's a function that describes the limits of the describable.
I've always wondered what a busy beaver function was.
Yeah.
So that's good to know. That's good to know. Of course, computability is a whole thing that, it's related to number, but in a certain sense, it doesn't matter because we can live in math land if we want to and say, computing is for computers, those funny people in the back room who just add up numbers. Or we can do what everyone likes to do and just say, let's consider, the number 4 an eminently computable number.
Well, I mean, that's true. If we're ignoring like the infinities or like, I mean, just, the square root of 4, square root of 2, whatever
also
it is.
computable, the square root of 4.
Oh, yeah. Sorry. Okay. But the square root of the square root of 4.
That
is
just an error sign.
Dang.
Though, right? If this
and then we're back to that whole.
Or if we were to compute forever, we would not reach it. And that's just outside the barriers of computable. We use infinity until we can get something closer. It's always going to here, there, be. So it's a meta concept related to this. There's probably ways to squeeze in a lot of these things.
Yeah. I mean, generally we define like, so like if you're like trying to rigorously have calculus and you're trying to make it quote unquote, well, instead of just hand waving of saying, well, this is infinitesimal and this and that. There's different ways of kind of deriving that, but the one that's usually like more commonly taught is something called it's like the epsilon delta formulation, right? And it basically says where it's like, well, I used to have it memorized, but it's something along the lines of like, well, we have these inputs and these outputs, and for anything of for any distance you can get here with like, if you can think of something that's like really, really close between these two, then I can think of something even closer by using something else, right? And so instead of like you're kind of going around, like you're invoking infinity here, but you're always doing it through like this specific example of like, well, given the biggest number, I can think of a bigger one, right? And that's how given this, like as close as you can get, I can get even closer, right? And we can, rigorously say this in these exact set theoretical statements or whatever. And then that's how you get to calculus and how you get to infinity. But even without that, when they were just saying, because this, nobody thought of this crap until, 100, 200 years after calculus is invented. And calculus worked just fine without that. It was just like, yeah, well, this is kind of infinitely small and you multiply by this and yeah, you get the answer. And like the answers worked. And, we can fucking figure out the orbits of the planets. I'll bleep that out, or just the processions of stars or whatever it might be. And we didn't actually need to drag infinity down to something that isn't infinite or that is, I can always have the bigger number. We could just say, oh yeah, that's probably infinity. To where in some sense, infinity might even be the more like intuitive concept before we find these ways of working around it.
My favorite facts about Mathland is that in Mathland, you get to make up whatever mathematical objects you want. So later, some guy came along, possibly several guys, and said, no, here's my rigorous mathematical definition of infinitesimals. So there, we could have done it that way the whole time. Yeah.
Yeah. Well, and those ended up paying off downstream is that if you use these rigorous definitions, then you can start doing things like you could take an integral sideways. And then if you start doing that, then you can start doing these calculations in probability that you couldn't do before. And then this cashes out to, like literally it cashes out to people making money. These things are useful and predictive. They work. So it wasn't just like a useless exercise. And it does have like valid predictive power in the real world when we're dragging infinity and describing it in the sense. So,
Right.
maybe these things are real.
Yeah. So here's something I want to ask you if it's real. How about 0?
I don't know. I mean, I guess 0 is obviously real as an operation and an object that works in certain operations in a language game that describe things. But then if we're saying, well, is that a number? Like, can there be 0 things? Well, I mean, I guess I can say that, and it kind of makes sense.
How many rocks do you have?
Why would I be saying that? It just seems kind of silly.
You say, I have no rocks. And the 0 is how we describe this situation. The concept.
Yeah.
Nan. We use nan instead of 0 to find out what.
Why would we do that?
It means this is not a number. A nan times nan is not nan.
So I'm thinking, in my collection of things, I have no unicorns. So how many unicorns do I have? A good answer to that is 0. So I think it's pretty safely a number as well.
Well, I feel like unicorns they imply something different than the rocks, because I could plausibly have
if you
rocks,
have no rocks, or if you have
and I just
no
happen
unicorns,
not to have any. But there's no way I could have any unicorns
not a question.
because there are no unicorns.
It's not a valid question. It returns an error. When you say 0 as the concept of if there were a number that described a not thing,
I think it
can't, then that would be the number. But not a good valid question here.
What?
Yeah, it's subjective.
What do you think is violated specifically by 0 being a number?
You have 0 goblins and you have 0 gargoyles
in this way.
And so if 0 is a number, then to describe the count of things that you do not have,
I'm with you so far.
Infinite amount of.
Okay, but if you have if I have in some other universe, say I have 1 unicorn and 1 griffin and 1 goblin and 1 centaur, maybe I have an infinite number of those things, so I would need an infinite number of paper, an infinite amount of paper as well. I get what you're saying. There's something strange about describing a thing and then but I don't have any, so I could have just described anything to you that I didn't have. But it seems that once you've described a thing, it does, in fact,
but in our
have a quantity.
All of a sudden, we have a unicorn.
And maybe that quantity is 0.
But we can do operations you can multiply by. You cannot divide by.
Right.
What if we conceptualize a 0?
I guess I see
still get our calculations
what you're. I guess I see what you're saying on that earlier point, at least, where if you think of numbers as occupying some amount of space or some amount of ontological reality in a way, then maybe you can only have a certain amount of the counting numbers. But if you add 0,
every number
then you can have as many zeros as you like. They're free.
It's a repeating fraction of 0 repeats.
On the other hand, if you just want to have a set of things in the colloquial sense, then as they say, there's only one the empty set,
and I have my
and
set.
That is the set that has
my
0 things in it.
Very different from your emptiness.
Yeah. I'm sure that's true.
So I'm thinking about, I guess, that initial thing I was talking about of just the union of wholeness and multiplicity. And I think
let's get into that.
Well, there's almost a sense where 0 is even more of a number than 1 if we're going by that definition, because, in 0, it's kind of the absence of both, as you have neither wholeness nor multiplicity, but then these absences can be combined, is that they are there's nothing here, there's no plurality, we're not even rising to that level, and so we're combining these things into a wholeness, the same way that you combine 7 horses into one thing, which is that 7, whereas 1 itself is, well, it's whole, but there is no multiplicity, and so it is in some sense harder to describe as a number if we're just sticking to that one definition. But maybe at some point we're just in kind of this weird language game where this definition just doesn't work for the later abstraction space, and so it's hard to even square them.
I guess it's it's the same thing. Zero is also a plural in English. I have 0 horses. I don't have 0 horse. But why do you think we ought to consider the union of multiplicity and wholeness as the definition of number, or some component of the definition of number?
I don't know. It just seems like that's what it is. Is that like if I'm counting, and I mean this is very like Platonic, right? Is like there's just a sense of we have these things and they have some commonalities, so I'm able to count them according to the fact they have that commonality. So it might be the things I have, or the things me, or the things in a certain space or something, right? But I'm counting them according to that commonality, and in that commonality, when I describe them, I'm pointing at one thing. I'm saying, okay, here's the here's the 5 golden rings or whatever, right? And those 5 golden rings, in saying that, I'm pointing to one thing, which is that group that is being specifically demarcated by the number 5.
You know what? I think this relates back to my skepticism of mathematical sets, because they have this idea in mathematics of a singleton, which is a set that just has one object. And, if you're reading along in your math textbook, you're like, that, what? No, it's just the object. It's not a set with one object in it. It's just the object.
Where the wife is going to be a single set.
Yeah, yes.
In our current league.
Yeah. Yeah. So I guess it's like, the singleton set of something is like, it's a very trivial group of it's like the identity multiplicity of the wholeness. It's like, what were all of the things in this multiplicity? Oh, just the thing, So
what about -1?
I'm comfortable with it as, the most simple number. That seems fine to me. Yeah. Yeah. Because I'm thinking, as everyone knows, you can very rarely have you can't have a negative number of actual things. And then you can have like negative money, of course. Sure.
Here we have a number.
So I guess,
it starts at 0 and it goes forever to the
maybe
right.
we're getting into a different sense of
the
number
same
there.
Thing, but we add
where,
the adjective negatively.
Sure.
And we lately cause it to go up and down by messing around with -1. By the way, with the square root of going imaginary. But could we potentially have a number of dimensions by?
I'm thinking about, the concept of number, or numbers, that is. I should stop. There is a big distinction between the concept of something, which is what you think about it, basically, and then the thing itself, which is maybe some sort of property or universal or something, and may or may not exist outside of the mind. But number has something to do with, like, how much or how many. So if there is any physical system that can have a negative amount of stuff when properly considered, then I guess I would have to throw up my hands and say, okay, I guess you can have negative things. And some people say electricity does that, but possibly that's just because we count the electricity wrong.
Mm-hmm.
And then you have, like we consider electrons negative basically due to a historical accident. And then, you have things like temperature, but then if you anchor your temperature to absolute 0, then all of your temperatures come out positive. So
I think technically you could still have a negative temperature that's like below 0 Kelvin, but then somehow this has all the properties of a really high temperature.
A black hole, the singularity is negative Kelvin.
But
and then you run math on negative Kelvin, and it'll do something. Say that does something, but maybe.
Sure. Yeah.
The temperature of a black hole is proportional to its area. Funny enough.
Huh.
Pretty hot.
No, black holes has a positive temperature.
I guess, there is time, or even just distance, where, as we've discussed, if you want to go forwards, that's positive, and if you want to go backwards, that's negative. And that's kind of arbitrary. But, can you recenter all of your time to be in absolute time? I guess maybe because maybe the Big Bang was the beginning of time. Can you center your distance to be absolute distance? I guess that's kind of like a...
You can't be in negative degrees west other times. So negativity is again, it's an adjective. I would have gone that one forward, but I did the same operation in a different way.
I think this...
So right is also...
Yeah.
I guess I would want to suspend this discussion because I can tell that this is going to dovetail quite nicely into the imaginary numbers, which are also, in Jason's view, kind of like, you're just describing a space and calling it, that's a number of something.
Yeah, 2D with rotation.
And, having your number line also go in the opposite direction seems like you're also just adding... Well, you aren't adding a dimension, but you're adding a different way that it could go. So I suppose we don't need to cover the rationals and irrationals if you want to get into imaginary numbers now.
I mean, are you saving the irrationals and irrationals for when you do the diagonalization thing?
No. I was just thinking okay, once we've considered whether integers are numbers, we'll consider whether rational numbers are rationals. And then we'll consider if rational numbers are numbers, and then we'll consider if irrational numbers are numbers. And then, of course, in the irrational numbers, you get the square roots, and then we could consider if the imaginary numbers are numbers, and the octernians.
I guess it seems like in a sense you're it's almost impossible to avoid this adjective trap because at any layer, if we're going from integers or just natural numbers to rational numbers, well, now we have to think about division. And then if we're going from there to irrational numbers, well, we have to think about square roots and powers, and then the negatives. Well, that's a negative thing. And I guess the question itself is, well, if we're even just talking about the natural numbers, aren't we really just talking about additions of one? And in some sense, is that like a prior concept? And then maybe this goes back to well, does 7 contain 3 or whatever the question was, right? But is number what we care about? Is it, can we just say, oh, well, that's the number 6? Or is it that, well, I had to count up to 6, and does that even make sense? Who knows? But
it wouldn't come out like any 6 acre do.
You could owe 6 acres of land.
You can write in your book that I had to some amount
right.
It came out to. At the same time, you could have, depending on your number set, you could have but I think that relates to a landowner being again an abstraction. It's you can't really measure because there's you could theoretically count out electrons or something. This is a very handy number to talk about areas, but and even I guess this is on a number line back those. But I still think different concepts. We're using a handy thing that we're familiar with, counting, scribe, marking out boundary map, which might have its own concept we could develop for it.
Yeah, I'm kind of I don't know, coming around to that position. If number in the sense that I've been considering it is just about these discrete counting numbers, and then the other stuff is really just distance or volume or a continuous magnitude, then that just means there are 2 types of numbers. But
J
or
you could kind of try to find significance about specific letters used for gematria, but it would absolutely not have any. But maybe I don't know. It is we're used to the numbers having for this specific relation. There might not be a way.
Well, it's obviously a very useful and evident relationship that if you have 1 yardstick and then you can measure something that's 3.5 yards,
you haven't
and it's 3.5 of the length of your yardstick, your 1 yardstick.
Right. It works, but the thing
sure.
is,
Sure. I don't really have a problem with that.
I'm just taking up, just waiting for Jay.
I'm gonna radically say yes to that. Yes, the thing itself.
I don't know.
Stand.
I don't have a strong. I think they're just kind of 2 different ways of looking at it. Yeah, it's hard. Well, there's a question if you can even take a stand at all. I think my reflexive view is that we're essentially stuck in the modern way of viewing at it, and any kind of way of looking at it prior to that is kind of like a LARP. Not because one is more correct than the other, but just because it's I'm a dirty historicist, and this is just the way language works. To where it's yes, I can understand that the way they use language means this, but I couldn't actually use the language this way in like content, like everyday context, because this is just the world I live in, and this is just how we think of it. And so, you know, it's hard to really take a stand, but it is there.
This is what you're talking about when I came in. Is there a deeper concept from which we derive both counting? And it doesn't seem that way. It seems like counting is primary. It is a thing that intuitive. You could try to make counting on something else, but that would be circular. You can definitely make area dependent.
Right. Well, I mean, I guess you could make area dependent on something else, but then like, how would you like? I can't imagine a human being like growing up to the point where they could like conceptually understand it, you know, to where, okay, yes, I can understand logically that area is actually this other thing, before they have understood the concept of like, oh, there's more water in this and there's water in that, right? Like it's there's a sense of it, or I guess that's volume, right? It's like, oh, this is bigger than that.
From here to there, from this mountain to that mountain.
Yes.
And you can add number and twice as far.
One's just going to look bigger.
But maybe there's other adjectives. I mean, well,
I was going to say, well, you can say it's as far as from one mountain to the other, and then you have to go back to the first mountain. And that's twice as far, even though you don't have a 2 in there.
Huh.
I guess you have an and. Yeah.
It's interesting. Well, and is funny, and this might be a wild digression, but I think about this a lot, is that and contains because there's other ways of kind of linking equivalent grammatical classes, right? Or just even like linking sentences. I mean, even though there's different ways of using and, right? So I can get like 2 independent clauses and I can string them together with and, or I can have like 2 nouns or 2 adjectives or something. And if I put an and between them, I'm saying like, okay, these are somehow equivalently important. But then if I'm stringing together things with and, if I'm stringing together independent clauses, there's kind of an ambiguity there, because you could just as easily get the same meaning from omitting the and, or sometimes the and will also imply the meaning of but or even or. And it's all just kind of baked into that use of the language, and you just kind of figure it out from the context. And then and is something that's just kind of there for rhetorical effect or the rhythm or something, or, you know, but it doesn't necessarily imply this if you're linking the independent clauses, to where if you're linking, you know, kind of dependent phrases, then maybe and has kind of its more like, you know, it has a more distinct conceptual meaning. But I'm forgetting how this tangent related, but that's always bothered me. God damn it! What is with that? Okay, I'm cursing again.
But is just an advanced and that implies that the second fact is like surprising. So there's half of your mystery right there.
Yes, but in some sense, it's fundamentally superfluous.
Mm-hmm, mm-hmm. And let's see, or it kind of depends on the context. I think if you wanted to really logic it out, there would probably be some stuff about like existential or universal qualifiers, and then depending on how you want to distribute like all that stuff, then ands turn into ors sometimes. And so depending on how the person is understanding the sentence, it might mean that an and or an or is warranted.
Is there a but? Does anything like this, like Zor or Nand or any of that, like, could any of those plausibly correspond to but? Because like and clearly has a logical equivalent. The and right. Or does, but
that's the funny part. In like your first semester of formal logic, you'll get sentences with and you translate them to and then you get sentences with but, and they tell you, listen, but just means and. Forget about it. There's like this spooky epistemic layer of pragmatics on top of but, you know, that's like, you have to go beyond first order logic and beyond second order logic and get into like Bayesian information theory before it makes any sense to start using some sort of but operator. Right. And I don't even think there is one.
Yeah, I mean, I guess like in Bayesian, like it's almost something like, well, here was a statement that was made, and you would think it implies this, but actually it's this other thing, and here's like this qualifier matting or this other thing, and it's right. But it has something to do with like pragmatics, like something about your intuition or the social context, because logically that shouldn't matter unless you were talking about like the probability of it, i.e. like how it's intelligible to you, how you interpret it, etc. So that makes sense.
Right. And if you use it as like a basic conjunction of nouns, then you could say I had, a horse, but also a unicorn. And that just means you have a horse and a unicorn. But I guess the but also is like, you thought I was talking about regular horses, but we're in crazy horse world where unicorns exist. You fool.
So it's really a way of calling people fools.
It's a shorthand.
Yeah, every
and plus
mathematical or logical concept involves calling people fools when I describe them.
related. And so we could imagine any number of other operators, including
it's you fool. This other thing.
You could add suspicion. I think we have some, not on that.
Mm-hmm.
True. You could say and suspiciously a cake. How do you get that cake?
I think, but actually, it can have a specific use to add suspense if you're using the not but operator. And I'm forgetting what this is actually called, right? But it's a construction, it's a phrase to where you say, not A but B, and then you don't have to put a comma between them because we understand we see not, and then we're primed for but.
Right. And in logic, logically, if you're saying not A but B, then you could really just say B, presumably. But the point is you might think I was saying A. So pay attention when I say B.
Within,
and how that's distinct from A.
As operator is kind of crowd control secondary to we were primed for.
Yeah. So let's see. Where were we before this digression?
Well, I'm forgetting where we were, but I do think that the idea of parsing out this pragmatic layer in language from what is simply reducible to logic has a lot to do with our discussion about number, and that it's kind of it's kind of isomorphic to this difference of I doesn't seem like a number, -4 doesn't seem like a number, square root of 2 doesn't seem like a number. But that's only they don't seem that way because of the pragmatic content, or maybe it's the other way around, right? Maybe it's if you ignore the pragmatics, then you can get hyper autistic and just say no, only this is a number, right? But then, they happen to be useful in these other language, who knows? But maybe there's something there that maps to the rest of it. I don't know.
Yeah, I think I see what you're saying. Even just talking about what the word number means, it's possible that when we get down to it, it's there are 4 different uses of the word number, and you just have to be okay with that.
The purpose of breaking
unless
this open
you don't want to talk to anybody anymore.
So that math isn't. Because math.
Yeah, I mean that's about where I'm at.
That's for the ancients, because we have.
Yes.
We have.
Yeah. No, I mean, I think most of higher math, or at least my experience learning physics was that, and I've given this take before, right? But it's I feel most of higher math is really just learning better notation to do complicated things, where the notations just kind of takes care of all of the thought for you, so that you don't have to think about it, and then you can just kind of look at the stuff you're actually interested in. And my favorite example of this is Einstein notation, which was technically invented by some other mathematician before him, but nobody gives a shit, so I cursed again. Nobody cares. We name it after Einstein because he independently derived it, and it's used in physics. And basically is that when you're doing complicated physics, you have all these matrices, tensors, whatever, flying around, and you have these big grids of functions to describe things. And you could equivalently describe those as a series of things being multiplied by another series of things. And then he didn't feel putting the little this is a series thing over and over, so he just started writing little indices on the symbols where there's a lowercase and the uppercase. And then if you see a lowercase or an uppercase, then you know that, this means that everything that these stand for gets multiplied together. And then you just put a bunch of these together. And then you've taken all of these, grids of numbers and series of additions, and you've reduced all of their abstractions into just, subscripts and superscripts, and you have little rules to follow for them. And then you can add other rules on top of them, and then you can start abusing them and doing all these tricks. And you can, subtract everything in this one by -1 and then add 1. And then, and you're getting all these things that would map to kind of these galaxy-brained ways of moving these grids around. And you've reduced it to this very simple little game that just happens to map to it. And it's just a better syntax, a better language. You're just more powerful. You can think better because all of the work is being done by this linguistic apparatus that was gifted to you by your forefathers.
Nice. Is it ever ambiguous, the Einstein notation versus the normal, I guess, capital sigma notation?
Yes, but you would only use it in situations where it's like the context is obvious enough for it not to be ambiguous. So, like, what you're not
Mhm.
writing is it's like, well, basically what you're skipping is saying like, well, okay, you have like a subscript U and a capital or superscript U, and if you were like being super autistic about it, you'd write like some, and then you'd write, well, U goes from 1 to 7 because we're talking about 7 dimensions of something or whatever, and you're just ignoring that because you're assuming the person already knows like how many U's there are or whatever and what they stand for. So it's that could be an ambiguity, but it's just kind of priced in. Usually just do it with stuff like usually it's just done with the 4 dimension of just space time, and then from there.
I've always thought it was a shame how mathematicians have to reuse all of these symbols in potentially ambiguous ways, but they had to, they needed to put them into a printing press made of real pieces of metal. So, what are you going to do? Say, "Oh, Mr. Printer, I need new pieces of metal." They'd say, "Get out of here." Although it is said that when Bertrand Russell and Whitehead were making their new book where they were finally going to prove that 1 + 1 = 2, they needed so many new symbols that they were like, all right, we're getting new pieces of metal and we're wheeling them down to the printer because we're just that cool.
Yeah, I guess they did have a lot of new symbols.
Yeah.
I mean, mostly just like the little U and the upside down U. What gets me there is that mathematicians love, like, okay, you use the Greek alphabet everywhere, but then you're also
Mhm.
using the Latin alphabet, which is based on
Mhm.
the Greek alphabet. And
Yeah.
so, like, half of these have some, like, corresponding equivalent where it's very difficult to, like, distinguish them, especially if you're like, some mathematician writing out on a chalkboard, and you probably you're a mathematician, so you probably grew up using like Cyrillic characters, so it's not like your handwriting to be good anyways, and so you just get this big stupid mess that everybody's expected to parse anyways. And I think that's downstream of the printing press issue.
Yeah. Well, too late to do anything about that.
Yeah,
So
keyboards made it worse.
true. Although digital printing has made it better because you can have as many symbols as you want. Really.
Well, you can, but then we don't.
Yeah. That is also true.
Yeah.
So do you want to talk about the rational numbers?
Kind of a silly name, isn't it?
Yeah, like, geez, you numbers think you're better than the rest of us, huh?
Yeah.
You think you're the only numbers that have discovered how to think. Oh, well, that all makes sense then. Yeah, yeah. Really, I have no idea why
Huh.
they're called like ratios to begin with. Maybe because you actually have to think about like, okay, this is like 2/3, so I just know by reason that there's a number here, even though I can't write it down. I don't know.
Yeah, it's relational. I mean, now I'm trying to think of a hot take where somehow like the just based off that Yud joke of like somehow the rationalists are in some deep way like against the irrational numbers, and they're kind of the like there's this Pythagorean cult, and in some sense they're
Leave
the
that in there.
continuation of it. Yeah, and then they have some enemy in the irrationals, but yeah, who knows? It's
Yeah. Pythagoras died from refusing to step on a field of beans. Work that one in there.
he died of deaths.
He did. He did. So yeah, I think the rational numbers definitely an answer to how much, if not how many, which of course is just an English. Our very concept of countability is just baked in there. So wouldn't make too much of a distinction from that, except that it's a distinction that made sense to various speakers over the years. Oh yeah, I was kind of thinking, like we were talking about. Well, you can kind of define area in terms of counting, but can you define counting in terms of something else? I think you can define counting in area, like or distance. Like that's how Euclid did it, I'm told. He wasn't like, here's a number. He was like, here's a little line that has some sort of distance. I'm gonna make some proofs about all these different little lines that I have here of different lengths. And then, what's the size of this square? Well, it's about 4 of these little lines that I have. What's the problem? So, and some would say that based on how physics actually works, which I still don't understand that. If anyone really figures it out for certain, let me know. They think that space is basically continuous, and then all of these discrete concepts we come up with are like abstractions on top of the continuous space. Although then they say things about like a Planck distance, which I'm not sure about that. And I guess it also relates back to rational numbers because, if at the bottom things can only be Planck distances from each other, then perhaps there are no rational numbers, and it's just a misconception, much like how your temperature scale can have a negative until you anchor it to absolute zero. Maybe you can have, rational distances unless you anchor them to absolute distance. So, Jason, tell us about the Planck length. What is it?
Now that you're talking about this, because we were talking about that whole thing about but and like pragmatics being divorced from something, and there's a sense that, in physics, you measure something and then it has some kind of variance, right? It's like, well, you measure something as plus or minus this. And, we can make statements, the uncertainty principle or something. Well, if you measure it to this specificity, then this one's going to be this one's going to be less bounded. And the Planck length is something like, how well you can know distance, or, whatever it is. There's Planck time, there's Planck whatever. I think it's interesting that there's almost a sense of pragmatics baked into physics, is that as you go to this deepest layer, then you get to these things where it's like, well, we don't know. And that's just part of like, here's the error bound. And this is somehow like integral to the calculations themselves, where like they're telling us this number and how sure of it we are. And, just at that scale, maybe it's necessary, but like, I would almost call that, like that's that third, like however layer of logic you need, where you start adding in all that Bayesian stuff, is you need the pragmatics baked into it. And so we've started with our concept of number that's based off maybe something, here's my horses and there's a social context and debt and blah, blah, blah. And then we abstract that out and we get away from it into, well, here's just this pure idealized space. And then, we notice that, if I shoot light at these electrons, they kind of start to jiggle and there's some energy that comes out and it happens to be at these same discrete chunks. And, all of a sudden we're back to needing these pragmatics to describe it again. And but becomes a real operator.
You've kind of lost me there. At the beginning, I thought you were describing like, there's always measurement error.
Yeah.
And that's pretty pragmatic. But of course, physics is often trying to pragmatically do things. And then I don't really get where you were going with the
I guess
discrete chunk of energy.
So it's the sense that in classical physics, while there is always measurement error, if you're talking about the physics classically, just in theory, right, just describing it mathematically, you don't need the error anywhere. The error just doesn't show up. Whereas if you're talking about like a quantum mechanical system, well, you're getting these probability distributions, and any answer you get, you're getting some kind of, the theory itself is giving you some statistics, and those statistics will say, well, in the aggregate, you'll see this, and here's the error bound on that, right? And here's how likely that is. And something like the Planck length is telling you, like, okay, well, if you try to, if you really don't care about the momentum at all, then you can narrow down the distance measurement to this much, right? But then here's your error, and it's just going to be fuzzy at this layer, and then your momentum is going to be totally unbounded. And so there's a sense where it's like the pragmatics is forced back into the theory, and without that, it would just be incoherent because it's inherently probabilistic.
Well, do you think that's how it really works, or is there some kind of, we just haven't gotten there yet? Like if I was a ye olde physicist or chemist or whatever, and I was measuring things, I'd go, well, sometimes it's 5 and sometimes it's 6. Who can say? But eventually we discovered it was, 5.324 or whatever.
I think my suspicion is something like the imaginary numbers used in quantum mechanics like correspond to something physical. So that would be like a wave function, where the wave function isn't just like this imaginary like nonsense thing that we use that, you square it and then it's this probability thing and it's real. That somehow that has like some physical properties that are like real in the world, because imaginary numbers are just rotation. Like it has to be real and they do something real. So that makes sense. But there's also that whole like Bell's inequality thing, and I used to know how this works better, but I don't anymore. But the verdict on Bell's inequality seems like probably it's just inherently probabilistic, and I forget how they have casually or causally like figured that out and then mapped it to like a coherent account of philosophy to where that makes sense. So I don't know enough about it anymore. I'd have to like relearn Bell's inequality. I haven't done that in 10 years. So
yeah. Okay. Yeah. I've there's a side question about like, is the universe deterministic or probabilistic? And my sense is, just my hunch, mind you, is, everything seems probabilistic on the surface. Like I'm flipping a coin and then it comes up heads or tails. And from my perspective, I have no idea which one it's going to be. 50% of the time it comes up as one and the other. And then sort of the story of science has been going into lower and lower layers of physical reality. Lower is a bad term, but smaller usually.
Yeah.
And then, everyone kind of thinks that the coin toss is completely determined by classical mechanics, and I just don't know enough stuff to know how it's going to flip. I'm not sure actually. I'm just assuming there that whatever quantum effects are completely swamped by the classical effects there. Yeah. And then so, I've cottoned on to this pattern. So I kind of think that underneath whatever probabilistic thing we seem to find, there's probably just another deterministic thing. But that's just a hunch.
Mm-hmm.
That's just a theory, a game theory, which incidentally makes me more receptive to the pilot wave theory of quantum mechanics, which I have absolutely no standing to make judgments about. But he's like, yeah, there is an electron in there, and it's definitely in one place, and we just don't really know where it is. It gets pushed around. Eventually, we find it.
I'm cursing again. You're gonna have to bleep out 5 things now.
It's okay. We're not gonna bleep them out. We're gonna roll on through.
Well, I don't know. I'm getting sleepy.
Oh no. Well, that can't be avoided. That's a natural human limitation.
It is. And I mean, I don't know. I mean, I think there's maybe something about that computability function where like, well, maybe in principle, like there could be something deterministic, but maybe like the way our brains are wired, like we're just never going to find it because we're all like linear piggy cells and we just don't have to describe it. Or maybe it happens to be like uncomputable and then that's like spitting out a probability somehow, but that doesn't really make sense. So, who knows? But it does seem like kind of yeah, that's a pattern, but in another sense, there's like a hubris to it. And there's also a sense to where it's like, well, if we're seeing this pattern, we're assuming that everything is, we're assuming it's all reducible to this mathematics or it's something like that, when the mathematics itself only makes sense in terms of like a linguistic description of cause and effect. And then the mathematics is a way of describing that. And so in some sense, at least, my hunch is that everything reduces to some kind of like, Aquinian, like atomist metaphysics or something, to where it's like, you're sustainer of things, and then they will something, and then this and that, and then blah, blah, blah. And then the math is something like way downstream. And then math itself is incoherent without some kind of linguistic description. But then that gets over to the kind of debate of, well, like, can computers actually compute at all? Or do they need us to project semantic content? Is semantic content real? Or is it something that can be like somehow magically derived from like numbers if they're like associated in a certain way and blah, blah, blah. And I have a very strong feeling on that, but some people feel otherwise. So basically abstracting out from that pattern. And so who knows? I need to finish reading Thinking Being there, but I suspect that the Catholics are right. That's my.
So you're converting to Catholicism then?
It's not. We'll see.
Well, I guess I would like to interject that I think some people say that like the whole universe is made of math or numbers or whatever.
Mm-hmm.
And numbers, I think, being a particularly egregious way of talking about it. Because I think, we have our math and our numbers, and they're like a human linguistic construct, but they describe something in the universe, which is like quantity and magnitude and things that numbers can describe. And you can also call that math, frankly, but it's a different type of math. It's like, I'm interested in what's really out there, and there is nobody writing the number 2 down in an atom. which is just something to keep in mind when investigating this stuff. But if you're getting sleepy, we can adjourn.
I think that'd be good. I think we're at about 2.5 hour mark on the dot. I think that's perfect.
Nice.
Nice. Because I know we did the Ava one, and that was like 2 hours or something, or one of them was. So yeah, I think this is good.
They can go as long or as short as they need to.
Yeah. We could probably do another 2.5 on this topic, honestly.
Well, keep your eyes peeled for number 2, the successor to Number. All right.
Well, good night.